Hello everyone, it is Dr. C. Happy Friday. So the pre-lecture for today will essentially be the last material for the exam next Thursday. And so the last two things that I really want to cover for the exam are strong bases and weak bases. All right, so we've already covered strong acids, weak acids, we've defined pH, we know a lot of things. So transitioning to strong bases and weak bases is not that different, except that bases produce hydroxide. All right, so that will affect our calculation a little bit. So let's, if I can grab a pen here, look at problem 3. This is on the part 2 handout for chapter 16. You probably picked this up in class on Thursday. If not, look in Blackboard and print out a copy. Now, you probably have used sodium hydroxide in the lab, maybe potassium hydroxide. You see that it has hydroxide in it, so you're probably thinking, oh yeah, that must be a base. Well, it's really easy to identify the strong bases, and they are the soluble hydroxide salts. All right, so everybody has solubility rules memorized from last semester, correct? Of course. But you might remember that most hydroxides are insoluble. Really, the only soluble hydroxides are the alkali metal hydroxides and then also barium hydroxide. That's it. Depending on what table you look at, calcium hydroxide's kind of soluble. Strontium hydroxide, slightly soluble as well, but we'll just ignore those for now. So essentially there's only 6 strong bases. All the alkali metal hydroxides, so go down the list, lithium hydroxide, sodium hydroxide, I'm not going to write hydroxide each time, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. Okay, and then when you get down to cesium, make a right turn and come over to barium. And those are the 6. Those are really the only soluble hydroxides. So when those salts, these are ionic solids, when they dissolve, they're going to give us a lot of hydroxide in solution. So something like potassium hydroxide is a solid, but we can dissolve that in water. It is a soluble salt. So remember back to last semester, what do we assume for soluble salts? Yeah, they dissociate completely into ions. So there's the cation, potassium ion, and the anion, hydroxide. So remember, ionic solid salts will contain cation and anion. All right. Soluble salts, we assume 100% dissociate. So this makes our calculation really easy. If our solution of potassium hydroxide is 0.5 molar, how much of it reacts? Say that's initial. What is the change? Yeah, 100%. All of it reacts. So just like a strong acid, strong bases are really easy to do our calculation for because we can get the hydroxide concentration directly. All right. Now this is hydroxide. We want to get pH, so we need hydronium. So one way to get the hydronium, don't forget this equation. Oops. Okay, so Kw is 10 to the negative 14th at 25 Celsius. Plug in hydroxide, solve for hydronium. Try that. Make sure you can do that. You need to know that for the exam anyway. But let me show you something new. From this equation, we can actually develop this relationship. Essentially, we take the negative log of this whole equation, and we end up with this. The 14 comes from 10 to the negative 14th, taking the negative log of that. Negative log of hydronium is pH. Negative log of hydroxide is POH. Okay, so this little p, this lowercase p, just means take the negative log. So POH means take the negative log of the hydroxide. So another way we could solve this is to calculate the POH first. Again, POH just means take the negative log of the hydroxide concentration. So take the negative log of 0.5 And here's my calculator. You can see it obviously. So this comes out to about 0.301 for the POH. We want pH, so subtract POH, and you're going to get pH is 14 minus the POH, which is going to give us 13.699, which you can still see there up at the top is choice D in this problem. All right, so a couple things to notice there. Strong base, highly basic solution. Our pH is getting close to 14. That's a pretty darn basic solution. But the other thing to know, just like, a strong acid would have a low pH, well, a strong base is going to have a low POH, meaning it has lots of hydroxide. High hydroxide concentration, low POH, but a high pH. Okay, so keep that in mind. So I think you'll like strong bases just like strong acids. We can get, since it's a base and it produces hydroxide, we can get the amount of hydroxide very easily and get to pH quite quickly. All right, next topic for this pre-lecture, weak bases. Now last semester, at least in my 151 classes, the only weak base we looked at is ammonia. Now, ammonia is a type of compound, or a class of compounds, that's called an amine, okay, or an amine, depending on how you would like to pronounce that. All right. Now, what is the common structural feature, or what we might call the functional group? What does that functional group look like? Well, it has a nitrogen with 3 bonds. Now, it doesn't have to be 3 single bonds. It could be a double bond and a single bond. Okay, or it could even potentially be a triple bond, but it has 3 bonds, 6 electrons. Since it only has 6 electrons, to complete the octet, we need a lone pair on the nitrogen. And it's very common for nitrogen to have a lone pair. All right, and that's really important because that lone pair can bond to an H+. So remember the Bronsted definition, a base is a hydrogen ion acceptor. You need to know that for the exam as well. So having that lone pair, remember a bond, a single bond is a 2 electron bond. So now we can form a bond to that H+. All right. So amines. Ammonia is the simplest one. And that's why we started with that. Plus ammonia is a very common weak base. Okay, 3 hydrogens. All right, but we can put different groups on there. All right, so look at this one right here. This one has, the nitrogen has 2 hydrogens, but it also has a CH3, which is called a methyl group. But same thing, 3 bonds, nitrogen with a lone pair. That is a weak base just like ammonia is. Okay, one of my favorite amines, and remind me to tell you my trimethylamine story in class, and I probably told you this last semester, but it's worth repeating because I still laugh every time I tell it, so hopefully you will as well. All right, trimethylamine. So now we have 3 methyl groups. All right, we can add various other groups to the nitrogen. Now, probably for this first exam to help you out, I might even draw out the structure and give you more information than that, just to kind of point you in the right direction. But that's how we recognize a weak base. Weak bases are amines. All right. As an example, another group that is quite common is an ethyl group, which is CH2CH3. All right. So if we had 2 hydrogens with an ethyl, that would be called ethylamine. This one up here with a methyl group is called methylamine. It's not that complicated. Okay, but you don't have to do the naming, but you do have to recognize your amines. All right, so methylamine, it is a weak base. The other thing that tells you it's a weak base, so when you're on an exam and you see Kb, oh, that must be a base. You'll notice that the Kb value is relatively small, 10 to the negative 4th. That tells you it's a weak base. All right, so let's get some room here to do this. So remember, practice writing some of these reactions. We've worked mostly on acids, so you should be familiar with acids producing hydronium in water. But bases produce what? Yeah, bases produce hydroxide. So again, hydrogen ion acceptor, it's the nitrogen there that's going to accept the H+. We're going to form its conjugate acid, so add an H+ to that base. There's the conjugate acid. But when water loses the H+, bases produce hydroxide. There you go. So notice, go back and look at the strong base versus the weak base. Strong bases are actually salts. They just dissociate and give us lots of hydroxide. The weak base is different because it's actually going to react with water, taking a hydrogen ion from water to produce hydroxide. But in either case, whether it's strong base or weak base, we get hydroxide in solution. So this one, since it's a weak base and we have a Kb, I think it was 4.4 times 10 to the negative fourth. Let's double check that. Yep. 0.5 molar to start. Okay. Now, this is going to lie pretty far to the reactant side, but we will produce some products, so this equilibrium has to go to the right. We're not going to get much product, but we will get some. And at equilibrium, 0.5 minus x, and x. You've seen this before. All right, so since this is a base, oops, that's not what I wanted to do. Since this is a base, we need Kb, not Ka. Ka is for acids, Kb is for bases. Same thing though, products over reactants. In this case, x times x squared, over 0.5 minus x. Now, this Kb, 10 to the negative fourth, it's probably small enough. So I would go ahead and make the assumption that our initial doesn't change much. So we're going to say the initial stays about 0.5. Very little of the reactant goes to product. That will help with our calculation. Again, our Kb value is 4.4 times 10 to the negative fourth. So take that times 0.5. Take the square root to solve for x. And we should get for x, let me write it down here. Gosh. All right, here we go. 0.0148 molar. And what is x equal to? Yeah, x is not hydronium. Acids produce hydronium. Bases produce hydroxide. All right. Now, a couple of ways to work it from here. You could plug into the Kw expression, plug in Kw, plug in hydroxide, solve for hydronium. I would try some of these both different ways just so you know how to do it. Probably the easier way, however, is to get POH. Take the negative log of your hydroxide, and I come up with 1.83. So low pH, basic, POH, basic. Low POH, basic. High pH, basic. So when we subtract this from 14 to get the pH, we will get a pH of 12.17. All right, so basic pH, as you would expect for a base. Compare that to the pH that we calculated for the strong base. The strong base was, I think, about 13.7. This is significantly less, about 1.5 pH units less. All right, so the weak base is certainly weaker. Now, as far as weak bases go, 10 to the negative fourth, there are a lot of weak bases that are weaker than that, if that makes any sense. But anyway, good to compare our pHs from that strong base to the weak base. All right, last thing for this pre-lecture, and I've already gone a little bit longer than I had planned, but it would be good to check our assumption, because that Kb value of 10 to the negative fourth might be a little bit close to that 5% rule. Now, checking the 5% rule, That's the same as calculating the percent ionization. So let's look back at our ICE table. We said that X was the part that reacted, or that went to product ions. Or in terms of the 5% rule, we said X was small compared to the initial. Part divided by the whole, that's a fraction. Multiply by 100 to get a percentage. And again, make sure you realize this is the same thing as checking the 5% rule. Is X small compared to the initial? But it's also the amount of reactant that ionized for this weak base. And let's see what we get here. So about 2.96%. Certainly meets the 5% rule. Less than 5%, we consider our assumption valid. The other thing to note, the larger your K value, the greater the percent ionization. We kind of started weak acids and now weak bases saying, well, a typical weak acid or weak base ionizes about 1%. But it does depend on what weak acid or weak base it is. And some are stronger than others. And this one, certainly not a strong base, it's still a weak base. It only ionizes about 3%. 97% stays as reactant. But it is stronger than some of the weak acid calculations that we have done. Obviously, this is a weak base, but in terms of percent ionization. All right. Well, I think that's enough. So on Tuesday in class, we will review strong base, weak base. We'll do a little bit more with weak acid calculations just to refresh those. Maybe talk a little bit more about POH. But this essentially gets us through what will be on the exam on Thursday. All right, good luck studying. Try to get prepared. I know next week is a crazy week for everybody, but then you get to relax for a while. All right, so struggle through, but struggle through with a smile on your face, hopefully. All right, I'll see you next week.